and start your presentation. Vadim, we see you, but don't hear.
Do you hear me?
Yes. Now
Okay.
it's okay.
Do you see the presentation?
Not yet. Please share your screen.
Okay. Just a moment. Just a moment. Так. It should be visible.
Yes, it's okay.
Okay. Yes, it works. My report is an efficient training algorithm of restricted Boltzmann machines. Introduction. Neural networks are used for solving wide range of applied problems. Neural networks are very flexible. They can be adapted for any type of data. Tuning neural networks parameters for problems is called tuning. So we have a training problem. Neural networks training requires a big computational resources. Neural network training can be formulated as optimization problem solving. The solution quality is an objective function. The objective function arguments are input data and neural networks parameters. So we have two methods for solving optimizational problems. First is gradient descent. We calculate the gradient of the objective function and move in the opposite direction. The main problem that we can stack at a local minima or into the inflection point. So we have a poor quality, but very fast convergence. The second approach is a random search. For example, genetic algorithms do not guarantee a convergence, but they can perform good in some cases. The second type of random search is annealing method. It almost guarantees reaching the optimal solution, but it's very slow. So I will show you new training algorithm based on the annealing Boltzmann method. Here the main steps. First is generate temperature sequence and initial solution. And second is perform the series of iterations, which consists of generate new solution, select changing parameters, and change parameters values. Then we make a transition into new solution, and at the end of each iteration, we check a stop criterion. Let's describe it in a more detail. First, we generate a temperature sequence according to the Boltzmann annealing. Here is the formula. It's quite trivial. Then we make an initial solution x0, which is random. We can use absolutely random solution. There is no limitations as in gradient descent. So we can just set zeros for any values. It's not a problem for annealing method. And the most difficult part is generating new solution. It's really complicated, and I will explain in more details. First of all, let's consider some neural networks features. Any neural networks consists of one or more layers. Depending on the layer of network, its individual layers can perform completely different transitions of the input data. Depending on this, the layer may consist of different fragments that perform completely different transformations. Any fragment of the neural network is specified by a set of parameters. Due to the fact that fragments perform completely different transformations, the corresponding sets of parameters have a completely different range of values. So we split the parameters into groups, strictly one group of parameters for one set. Then we generate a random permutation, as you see on the presentation slide. For each group, the length of permutation is equal to a set size. Then we generate a random discrete numbers, A1 and so on, AN, where N is a number of groups. Then determine the amount of parameters which would be changed in each group. First, A1 and so on, AN elements define the indexes of changed parameters at the current iteration. So once we selected the parameters to change, we have to change them according to such formula. We generate a uniformly random distributed variable on a segment from -Li to +Li. Li is parameters of the algorithm. For each group, it's different. Then we added this real value to the current value of the changing parameter. Then we obtain a final new solution. So we have to make a decision to accept the new solution or not. If the new solution is better than the previous or the same, we always accept it. So the probability is 1. If it's not, we calculate the probability of acceptance according to the formula on the slide. Next, we decide to stop algorithm or continue iterations again and again. The stop criteria is trivial. When the time for training is over, the algorithm stops. Otherwise, we continue our iterations. The most interesting fact that this algorithm converges in probability to optimal solution from any start point. Second, it's rather simple to implement, and there is no limitations to objective function. It should be just calculated easily and no more restrictions. So we made an experiment with this algorithm. The proposed algorithm twice better than gradient descent in quality. And this proposed algorithm has the same speed as gradient descent algorithms. So it's a very good result, I think. As a conclusion, proposed algorithm has significantly improves state-of-art training algorithms. Proposed algorithm can be used for training an arbitrary neural networks because it do not have any limitations for neural network architecture or objective function. So it can be easily adopted for any type of data, any type of neural networks, and so on. I think it's a good idea to implement it to different applied problems. So that is all. Thank you for attention. If you have any questions, please ask me.
Thank you very much. If anybody have questions, please. Vadim, please switch on your camera. We would like to see you.
Okay, just a moment. Just a moment. Так, screen. Yes.
Okay, maybe yeah. I will start. I'm not too similar with Boltzmann machines. Of course, I have read about them. The question is, when we deal with neural networks, in many frameworks, we can use dropout neurons. That means that we randomly can change structure of neural network. So can we use the same training algorithm in this case? I mean that in each step, with new portion of data, we will have another structure, another set of weights and so on.
It's rather interesting question, because dropout technology means that the architecture contains too much weights or too much neurons. When the values are close to zero, we can just throw them away and reduce the neural network size, and computational resources will be saved. This algorithm for now do not supply this method, but it can be, I think it can be adopted to this algorithm. I think it is possible.
Okay. Questions, please. As we usually say, if there is no questions, that means that everything is clear, or vice versa. Well, nevertheless, thank you very much for your report.